Swayam Prabha. Digital India. Educated India.
I can employ the Duhamel integral here as well to find out exactly the same solution. Okay, and let us demonstrate that. How do we get that? So remember, my PT here is P naught. It is constant. And what is my expression for the response at any time t? For an undamped system, it is m omega n 0 to t p tau times sine omega n t minus d tau d tau. One thing that you need to be very careful here, the integration variable here is d tau or tau, not the t here. So do not get confused. Okay, we are integrating with respect to the integration variable. Okay, integration variable here is tau, not t here. Okay, so that you need to be careful. Now, what is my p tau? If I had a function here, I would substitute t equal to tau to get that function, but this p tau is now constant. So pt is constant for any time. So p tau would also be p naught only. Okay, because it's not a function of t. It is not varying with time. It is constant. Okay, so all I need to do is to find this out is to substitute here this expression 0 to t. P tau is p naught sine omega t minus tau d tau. Okay, so I can write here, and I need to integrate this sine omega n t minus tau. Okay, what is the integration of sine omega t minus tau? Remember, I'm integrating with d tau here. It would be integration of sine is actually minus cos, but there is an minus sign, okay, next to the tau here. So minus minus would get plus. So the integration would be cos of omega n t minus tau, and the coefficient of the integration variable will come in denominator. Okay, so this I get as cos of omega n t minus tau omega n, and then I need to substitute 0 and t, the integration variable. And if I do that, I will get in p naught m omega n square 1 minus cos omega t. Okay, this is what I will get. Now remember, m omega n square is nothing but k. Okay, k is equal to m omega n square. So this I will write as p naught by k 1 minus cos omega n t. So although I have taken, like, a large number of steps just to demonstrate you, I could have directly written this and calculated it in one step. Okay, but I just wanted to show you. Okay, it is not as difficult. So if you look at it, this expression using the conventional method and the expression here using the Duhamel integral comes out to be the same. Okay, and we can utilize any of these method to find out the solution. So basically, let us come to, if I have a step force, okay, which is a load which is applied like this, the response to this step force ut is nothing. How would you plot this? This is, remember, it's a function which is oscillating, but it is now shifted by p naught by k. Okay, and what is p naught by k? This is the peak static displacement subject to the load p naught. Okay, so I want to plot this function, and the plot of this function looks like, if let us say this is ust naught. Okay, so this is basically your ust naught. Okay, equal to p naught by k. Okay, and this function is actually varying about, oscillating about in this. All right, this is my u of t. Okay, now in this case, remember, when you had a harmonic force, usually if you apply a harmonic loading on a single degree of freedom system, your initially, if the system was undamped, okay, your system had both natural frequency and the harmonic frequency. That is the excitation frequency, both component. Here, because there is no frequency anything, because it's a non-periodic loading, okay, the structure vibrates at its own frequency. So ut vibrates at own frequency omega n, okay, around ust naught. Okay, so with this load pt, okay, this becomes my equilibrium position, because remember, you are pulling the force, you are applying the load p naught, so the force or the system would deform, okay, and if you keep the load constant, it would vibrate around that point, okay, around the force p naught. All right, now same expression I could also derive for damped system, so that my equation of motion is now cu dot ku is equal to a constant force. Oh, okay. Now again you can employ Duhamel integral to find out what is the, okay. Now I'm directly writing down the final expression. Okay, so you need to integrate this t minus tau, and then you have sine omega d t minus tau d tau. So you can directly employ this expression to find out the response to this. However, it's not an easy integration to do, and you will find out. I encourage you to actually do that integration. Okay, this is one of those integration which comes out like, what is called the repetitive integration, in which I comes out to be some function times some constant times I. Okay, so you have to calculate, bring I to the left, and then you calculate it like that. When you integrate it, it will come out to be like that. In this case, it is just easier. Okay, so let me first write down the expression. After you integrate it, I'm going to write down the final answer, but I encourage you to do this integration and see how difficult it is, whether you find it easier or difficult. Okay, and then you compare it with the conventional method. Okay, so this I can write it as ust naught, which is again p naught by k, times 1 minus zeta omega t cos omega t zeta. So this is the expression that you get for the step force excitation of a single degree of freedom system or a damped single degree of freedom system. Okay, if you wanted, you can employ or you can utilize the conventional method of, okay, solution, which you know that ut you can represent as, for this system, okay, particular solution plus complementary solution. Okay, now particular solution would be p naught by k again, and complementary solution of a damped system is of this form, isn't it? It is a cos omega dt plus b sine omega dt. And given the initial condition u0 equal to 0 and u dot equal to 0, you can find out these constant and get the same expression here. And it becomes like, it comes out to be much easier following this method here. Okay, rather than following Duhamel integral. So you have to evaluate in these cases, you have to evaluate your options, that which is coming out to be a better option to find out the response of the system. Okay, now if you try to plot this expression for a damped system, what you will see, okay, I'm going to again do the, this is pt, okay, force p naught. All right, the response ut to this function, I'm again going to write for undamped system, it was without any change in amplitude. Okay, so this was undamped system. In damped system, if you look at it, there is a exponential negative sum. So it starts with the similar kind of motion, but then it decreases in time. The amplitude actually decreases in time, and then it actually converges. If you look at this expression here, after a sufficient time, this expression would become 0, isn't it? Because you have e to the power minus negative. So this expression would become 0, and ut would converge to ust naught for time greater than 0. Okay, if it's very large time, it will converge to this expression. Or the second way to do is that you give a lot of damping into the system so that it converges to UST 0. So all I need this term to be very large. Either I can do it by increasing the time or after sufficient amount of time, or increasing the value of damping here. Okay, so that it converges to UST naught. So let me give you a practical example of this. If I'm designing any system. Let us say I'm designing a platform on which people are like, jumping, or I'm designing any other kind of thing. Let us say I'm designing a digital scale in which I don't want a lot of vibration after I put a weight on it. For this type of situation, okay, where the loading is represented as a step loading. Okay, so if you jump on a platform, it is a step loading because you have load mg that you apply suddenly and then you maintain that load mg. And same is the case for a digital scale. Okay, in those cases, okay, if you want the system not to vibrate too much, okay, what you can do, you can increase the damping so much that the system comes down to rest very quickly. Okay, that is for the cases where it is under damped. Many of the cases, many of the situation, what happens, those system you make over damp, so there is no oscillation at all. So you increase damping so much, like damping greater than equal to 1, so that it becomes an overdamped system and there is no oscillation, it directly comes to rest. So in those cases, even if you apply a step force like this, okay, there won't be any vibration. So what do we learn from this? Whenever you apply a force, okay, whether it's a step force, any other force, whatever your static displacement is, okay, and remember, how do we calculate the static displacement? It is whatever the pt divided by k. This is the time variation of static displacement if I had considered that system has no mass, okay, and it basically varies with the applied force. So this is my static displacement. Okay, it will follow this if there is a static displacement. However, because there is mass and stiffness in the system, it actually vibrates around this static position. Okay, and depending upon whether there is damping or not, this dynamic response is going to either converge to this system or keep on vibrating about the static equilibrium position. Is this clear to all of you? Anybody has any doubt up to this point? Let me know.
Hello, sir.
Yeah.
In the periodic, then there won't be resonance won't be there in this case.
Yes, because see, structure, if you look at the loading here, remember, resonance happens because of frequency, isn't it? One frequency matches with the other frequency.
Yes, sir.
Now,
Yes.
we still have the structure frequency here, but applied load is non-periodic or non-harmonic. So there is no frequency of the applied load as such. Okay, so there is no resonance in this case. Okay, except for one case we will see later, where we have a half sine pulse. Okay, so a half sine pulse still has some period, isn't it? It has some period, and if
Yes.
that matches with that, then so apart from that, for arbitrary excitation, we don't see any kind of resonance or anything like that. Okay.
Okay. Okay. So we can say that structures which are subjected to the non-periodic forces are we can say that those are not tending to the resonance. So
They would not lead to resonance. Resonance is the phenomena that occurs when you have large amplitudes due to the frequency
forcing
of the
frequency.
structure. Okay, when it
Yes.
basically come close to the natural
Natural
frequency of the
frequency.
system. Here, because I have non-harmonic or non-periodic motion, it's nothing like that. Okay, those
Okay.
would not occur, except for the one case where the loading is actually like a, when we will discuss that, where loading is actually like a sine pulse. Okay, so it is not
Okay.
like a harmonic loading, but it is a sine pulse. Okay, and there is still a possibility that if this time period here, or time period by 2, matches with the frequency of the structure, then it might occur. Otherwise,
Okay.
no.
Okay.
Okay.
Okay. Thank you, sir.
Yeah. Anybody else? Any question up to this point? If not, then let me just introduce you to another commonly occurred loading that we encounter, and we talked about that, which is called the ramp loading. Now, I said that we talked about this step force, right? In reality, step force is never possible. You cannot apply anything suddenly. A step force is nothing but a ramp loading, which is like this, so that this time here is very, very small. Okay, so ramp loading is a more generalized representation of a step force or step loading. Okay, so ramp loading is basically if I want to apply a load P naught, so I want to apply a load P naught, right? And instead of applying it suddenly, I do it over a certain time, okay, which is called the rise time of the force. Okay, rise time is the time taken to reach the force amplitude that I want to apply. Okay, so this is a ramp loading like this, okay, in which I'm applying a force P naught, okay, over a time duration TR, and then I keep the load constant. Okay, so I keep the load constant after time TR. So my PT is basically, how can I represent this linearly increasing load here? Can I write this linearly increasing load P naught T by TR for T smaller than TR, and this is equal to constant force P naught for T greater than TR. This is the representation of the ramp loading, that up to the linearly increasing part, it is P naught T by TR, so that when T equal to TR, this force becomes P naught and then it stays there. Okay, and depending upon the value of TR, okay, again, this was a question that I gave to you in the very first class. Okay, depending upon the value of TR, we are going to observe the dynamic behavior of the system, whether there is a lot of oscillation or where there is not any oscillation. Okay, that all depends on this important value TR. In fact, it depends on TR by Tn, which is the time period of the system. But for the time being, let us say TR is a very important parameter that determines how the response would look like. Okay, and first we are going to focus only on this part here. Okay, so only the linearly increasing part where the force is still increasing. Okay, so for that case, my equation of motion for an undamped system, of course, is okay, P naught T by TR. Okay, this is my equation of motion. Okay, and I can go ahead utilize the either Duhamel integral, or I can utilize the basically the conventional method where I write UP of T is equal to this force PT divided by K naught. So this is T by TR. Okay, and U complementary for this would again be A cos omega nt plus P sine omega nt. And I can write my total solution as, remember this is P naught by K, okay, TR plus A cos omega nt plus B sine omega nt. Remember, you can use the Duhamel integral for that as well by assuming P tau here now would be P naught of tau times TR. Okay, and integrate it, okay, from 0 to T to find out the value of UT. Or you can use this method, whatever is convenient to you. In this case, I'm again going to utilize U0 equal to 0 and U dot equal to 0 to get the solution as P naught by K. Okay, so I can write the solution as P naught by K T divided by TR minus sine omega n divided by omega n TR. This is the expression that I get. Okay, now if you look at it, if I have this PT here, how would my UST would look like? The static displacement, it would be simply PT by K, isn't it? So this is not PT here, this is displacement here. Okay, UST would look like something like this. Okay, whatever the PT divided by K. However, this function, the second function, is a sinusoidal varying function at frequency Tn, at frequency omega n and time period Tn. So when I add it, these two functions together, the total response actually looks like this. Okay, so the internal response is UST of T. Okay, where UST of T is nothing but whatever the force times K, which is P naught by K times T by TR. This is constant here. This is basically UST is a linear function of T, so that it looks like this. And then the second part is actually sinusoidally varying function. And when we add this, basically I get this something like. And I still not have considered what happens after this point TR. We will see that in the future class. Okay, but I'm saying this is basically looks like this. So when I apply this ramp loading, basically system would follow the force. Okay, and depending upon the expression omega n tr, which is basically can be represented as 2 pi tr by tn. So remember, this is coming as my important variable tr by tn here. Okay, depending upon that, it might look like something with very less vibration, or it might also look like something like this. Okay, so it follows the static displacement curve. All right. And how much of the vibration it has around that static displacement curve, that depends on the omega and tr. Because remember, this is going to decide how much this sinusoidally varying function is reduced by. Okay, so that is going to be decided by omega and tr. Okay, which is basically tr by tn. Okay, so this is the first part when the force is still linearly increasing. We will see in the next class what happens after that. Can I say at this point, whatever the response that I obtained from here, so whatever the u of tr and u dot of tr I obtain, that would work like an initial condition at this point. Okay, for solution to this expression. This I already know. I have already derived in the first one. So what I'm saying, if I have something like this, I can represent the solution as response to this triangular linearly increasing function plus response to this step function. Okay, and this how do I find out? I find out basically u of tr and u dot of tr. Okay, so that with this condition, this would be a free vibration after this point due to this initial condition plus a step force, okay, at time t equal to tr. So I'm going to add this up and then further I'm going to find out the response. But that we'll do in the next class. Up to this point, do you have any doubt what we have obtained the solution to linearly increasing force and what is the static solution, what is the dynamic solution? Let me know if you have doubt, or otherwise we are going to continue this, okay, in the next class.